So we'll talk about biochemistry today, and like I said, over the next several weeks. But I just want to start with this. So what does this have to do with biochemistry? Sophia?
Because it's the stuff inside of the ice cream.
It's what?
It's the ingredients to the ice cream.
Okay.
So,
The ingredients of ice cream are related to biochemistry. Got time?
Alright, so the ice cream is made with milk, and milk comes from a cow, and cow is a living thing. So.
True. Okay.
what
What else can you tell me? So all of these are both dairy products.
Yes.
What else? How else might we connect this to biochemistry, specifically human biochemistry? What's that? Oh, we do. Do all of us consume them?
No, my mom doesn't.
Why doesn't your mom, Grace?
She's vegan.
Okay.
Lactose intolerant.
All right, Luke, what?
Lactose intolerant.
Lactose intolerance. What is? Tell me about that.
That's when your
So
body
you
All right, shh. Luke, go
you
ahead.
can't consume dairy products or else bad things are gonna happen.
All right. Why?
Katie's like,
So why is that? Why is that the case? So, Katie.
Like your body can't digest lactose, it's not really just dairy kind of, it
Okay.
just can't digest it.
What exactly is lactose? It's in milk, It's a sugar. So any chemical that ends in the suffix OSE is generally a sugar. Glucose, fructose, sucrose is table sugar. Lactose is another one. And so you're right, Glenn. Lactose is a sugar. It's found in dairy products. Katie just told us that sometimes people cannot digest those. So lactose is a sugar that it's a disaccharide. We'll learn about this in a few days. But that means it's not one simple sugar like glucose is. It's made of two sugars bonded together. In order to actually use that sugar and get it into our body and our cells, it has to be what? Digested or broken down. How does our body break down complex substances? What? Yeah, specifically, I think I heard somebody say it. Well, acids do some of it. Protein, a special type of protein. No, a special type of protein. No, not quite. Enzymes. So enzymes are a type of protein.
Is it laxative?
So this is milk that is lactose free. So it's specially prepared milk that does not have the sugar lactose in it. How about this?
There's pills that you
Those
can
are so these are so this is medication. I guess it's called, you consider medication, but that a person can take. That what does it do?
It helps break down the
Yeah, it helps a person. Yes, it helps a person to break down lactose, which their body doesn't do on its own. All right, so if I were to ask you, what percent of people, just in general, out of the population on the earth, what percent of people on earth are lactose intolerant? Raise your hand. Give me like a ballpark to the nearest 10% or so. Cece? 20% are lactose intolerant. Gaetano? About the same. Anybody have a very different estimate, Brian? 10%? Katie? 45? Sophia? 75? All right. So we're all over the place.
We got from 10 to 75.
The actual number is about 70%.
Well, maybe I'm lactose intolerant. I just don't
So about 70% of individuals do not have what we call lactase persistence. Lactase persistence means you can digest lactose. So, this is a map of, obviously it's not the entire world, but of Europe and Africa and Asia and Australia. And the colors represent something about lactose intolerance. What can you, I didn't include the he on purpose. So if we look at this map, can anyone infer like what color means what in terms of lactose intolerance? Gabe?
The more, it seems like the more, to me, it seems like the more red it gets, like the higher population of lactose intolerance.
Lactose intolerance?
Yes.
Okay.
And then like the more blue it seems like you get, the more lactase resistance.
Okay.
you get.
Other ideas, Grace?
I think it's like the opposite, like the red, like you're more persistent.
Okay, so you think red means can eat lactose?
Yeah,
And blue means not?
yeah.
Okay, what information are we using to like come up with this? Yeah, but what about the map is given Brian?
Maybe like people in the red, like they don't drink milk as much.
In the red don't drink milk as much? Look at those maps. So what if you imagine like those areas and what you know about sort of culture in these various parts of the world, it might clue you. And Ian, what do you think?
More shepherds and people who drink milk in red regions versus the blue regions.
Okay, so what do you think of the red means?
That you can tolerate lactose.
Okay.
That's what
That you
Yes.
can?
Yes.
All right. Because you're thinking in relation to agriculture.
That's what I'm more.
Okay. Cece?
Milk and tea.
What does tea have to do with it?
She's right now, it's all
Okay.
red.
Milk
Milk is
and
not an animal.
tea and okay.
But a
Okay.
lot of it's like
All right.
It's not
Katie?
related at all.
Like, you see that, like, on the blue, it's kind of like the coasts and, like, a lot of islands, and because, like, their diet doesn't include that much dairy, like,
Okay.
mostly,
They include lagoons.
it's like,
Thank you.
it's kind of like their diets don't include as much dairy as people, like the UK used to.
Okay. So if you know anything about sort of local diets, people on the coast, maybe main sources of protein might be fish and seafood and so forth. Maybe there's not as much milk consumed in those areas. Those are all good ideas. Yeah.
Okay, the red means that there's less cows in
Okay. So why do you say that?
there. Because over in Europe, there's probably less farming land because it's like more, the population is more condensed.
Okay.
So maybe there's less.
Okay. All right. All interesting ideas. What I will tell you. All right, Sasha. Last comment. and then we'll-
Okay, so, I think, like, maybe someone said this, but, like, let's say, like, the red could be, like, so, like, it goes, like, red to blue, and, like, the red could be the place where there's more people who are, like, intolerant, and then the blue, like,
Okay.
opposite, and, like, blue would be a place where more people are intolerant in that specific area.
Okay. Well, some of you are right and some of you are not. So I'll just give you this little bit of information, because we're going to talk more about this as our unit goes along. But the blue areas, the bluest areas represent the most lactose intolerance. Red areas represent the most ability to digest
They
lactose.
have to be able to have their milk and tea.
And we'll talk more about this as we move on. All right, but let's get on with our notes here. So that's just a little introduction.
Thank you, Mr. Ross.
Now, this is sort of a sad exercise in my other classes. Let's hope it's not as sad.
I'm sorry, I forgot. I'm not
So-
gonna lie, I forgot everything.
No.
I know
Oh, I know this.
that, thank you, Jack, hold on, please save that to build up my self-esteem as the class
I
goes
didn't
along.
know it back then.
So I know that I had all of you and minus one of you in 7th grade accelerated science.
Hey.
And I know
Directed towards me.
that we went over the vast majority of this information. And so I'm hopeful that many of you will be able to answer the questions that I'm about to ask.
Just to know something straight up. I didn't know it back then. I'm not gonna know it.
So let's talk about, first of all, just some real basic information about chemistry. So first of all, the atom itself is mostly empty space. And Rutherford was the scientist that sort of defined this and did the experimentation that showed by sending alpha particles at a gold foil and seeing how many bounced back. What he found is that the vast majority went right through the gold foil because they weren't encountering a nucleus. That the vast majority of that gold foil was just empty space. Every once in a while, an alpha particle would hit the nucleus and bounce back, and he recorded that and used it to estimate the size of the nucleus. And he found that the nucleus is very, very small in comparison with the entire atom. So the nucleus itself is made of protons and neutrons, and then electrons are in a cloud around the nucleus at quite a distance, actually. So protons, neutrons, electrons are what we call subatomic particles. An atom itself is basically the building blocks of the physical world. All matter is made of atoms. And that includes living things, non-living things, solids, liquids, gases. All matter is made of these tiny units called the atom. So let's talk about each of these subatomic particles for a minute. Proton. So a proton is found in the nucleus of an atom. What is its charge? Sophia? Positive. And, well, let's go down the columns. How about a neutron? Raise your hand, please. Luke? It's neutral, has no charge. Jack, how about an electron? Negative charge. Okay. Like all matter, these subatomic particles have mass. We use a special unit to signify the mass of these tiny, tiny subatomic particles. You remember what it's called, Brian? Yeah, AMU, atomic mass unit. So what is the mass of a single proton in AMU? Aiden? It's 1. How about a neutron? Gabe?
No, it's 1. It's 1.
Yeah, it's 1.
It is 1.
Yeah.
Come on. How about an electron? 0. Now, it actually, it does have a very tiny amount of mass, but we just sort of ignore it because it's so tiny.
That's sad.
All right, good. So you guys are making me feel much better than my other classes. So how do we, if we're looking, this is a periodic table entry for oxygen. It gives you some information. The atomic number, the atomic mass, the symbol, the name, electron configuration. So if we are looking at a periodic table entry such as this, and we want to know how many protons an atom of oxygen has, how do we figure that out? What would tell you the number of protons in this atom? Vlad? No? Gaetano?
The atomic number.
The atomic number. 8. So the atomic number tells you the number of protons. How about the number of neutrons?
15.
Right? No? Okay. How do you calculate it? No?
It's the atomic mass minus the
Atomic mass minus the atomic number gives you the number of neutrons. Now in this case it is 8, but it doesn't have to be the same. And finally electrons.
20 something minus.
No, it's 26.
Protons minus neutrons.
We're just saying, we're saying random words.
Mr.
We're just vomiting words. Let's think about it for a second.
26.
No, it's always
7.
The electric.
8. That's not 26.
Oh, it's 2.
It's always
It's not 26.
or both.
It's
It is 8.
That's what I said.
Atomic
Almost close.
number is the number of protons, but it's also the number of electrons, because atoms are generally electrically neutral. So the protons and electrons are balanced out. So the same number of protons, same number of electrons. Luke?
2 and a 6 group.
That's the electron configuration. It tells you where those electrons are located. There's 2 electrons in the first energy level and 6 electrons in the second energy level for a total of 8. So the electrons can be found at various, we call them energy levels or orbits or the electron cloud. And it starts close to the nucleus and then they fill in with electrons. The first shell is very small because it's close to the nucleus. It can only hold a maximum of 2 electrons. Then the other shells can hold 8 each. And 8 is kind of the magic number when we're thinking about atoms and how they interact with each other. Really, they're not circular orbits like this. Scientists believe they're more like these sort of strange looking clouds. And an electron is never really in one spot or another. We can't know where it is. It's called Heisenberg's uncertainty principle, that you can't simultaneously tell the speed of an electron and its position. That's beyond what we need to talk about. So the periodic table shows you a list of all known elements. We're not really going to use it in detail like we did in 7th grade, but hopefully you remember it. We want to define some terms though. So I just mentioned that atoms are generally electrically neutral. Their protons and electrons balance each other out. But sometimes that's not the case. Sometimes an atom will gain an electron, or it might give away one of its electrons to another atom. And that changes that, and that takes the charge out of balance. If an atom gains an electron, what does its charge become? Negative. It has another electron, which is negatively charged. If it loses an electron, it becomes positive. We call those ions. These charged atoms that have gained or lost electrons, they're called ions. And if you remember on the back of our periodic table in 7th grade, we had a chart of radicals. Those are also ions, ionic, polyatomic ions. The outermost electrons in the atom are called the valence electrons. The electrons in the final outermost energy level. Oh, this is just showing sodium becoming an ion. It has this one electron in its outer shell. If it loses it, it becomes a positive sodium ion. And these valence electrons in the outer shell, those are the most important electrons. Those electrons determine how this atom interacts with other atoms. The inner shell electrons are not nearly as important. So when we're looking at an element, we will often talk about its oxidation number. The oxidation number tells you how many electrons it wants to lose or gain. Because all atoms want to be stable. And stable means, for the most part, an outer shell of 8 electrons. Calcium, for example, has 2 electrons in its valence level. Okay, that's not 8. So how could it become happy, become stable? It could get 6, but that's kind of hard to go and find 6 other atoms.
Just get rid of those 2.
If it got rid of those 2, then the next level down is full, and then it would be stable. So it has a valence of an oxidation number +2. There's 2 extra electrons it would love to get rid of. Chlorine has 7 electrons in its outermost shell. 7 valence electrons. What would it like to do? Gain 1. It's missing 1. Its oxidation number is -1. So, since it's missing 1, okay, and since calcium has 2 extra, 2 chlorines can get together with 1 calcium atom, and each chlorine atom borrows one of those, then they're all happy, they're all stable. And we have calcium chloride, which is a compound, a stable compound. The number of protons, oh, here's an example. So the atoms, all atoms of oxygen, for example, they all have 8 protons. All atoms of hydrogen have 1 proton. All atoms of helium have 2 protons. The number of protons doesn't change for an atom. However, the number of neutrons can change. And that's what isotopes are. Here's an example of 3 hydrogen isotopes. They're all hydrogen because they all have a single proton. This protium isotope has no neutrons. This one has 1 neutron. This has 2 neutrons. They're all hydrogen, but they're different, what we call isotopes. And carbon, for example. The vast majority of carbon on Earth is carbon-12. 6 protons, 6 neutrons. But there is some carbon around that has an extra neutron. That's carbon-13. There's some carbon that has 2 extra neutrons. That's carbon-14. Often these heavier isotopes are also radioactive. They're unstable. They will break down and decay, releasing energy. Finally, isomers. So when I ask you for the chemical symbol for water, what is it? H2O. How about carbon dioxide? How about glucose?
Ah, I
C6H12O6.
Yes. C6H12O6.
Boom!
So what you are giving me there are molecular formulas. So this is butane, C4H10. This is also C4H10. Are they the same thing though? No. So when you give the molecular formula with the numbers, you're basically just giving the ratio of one element to another. These structural formulas give you more information about how those atoms are actually bonded together. So our focus here is biochemistry, the chemistry of life, of living things. So that's sort of a subset of chemistry. When you go to college, you might take a class in biochemistry. It's an entire class. And it's basically the study of the chemical substances and how they relate and interact to living organisms. Most of the matter in living organisms is composed of just 4 elements. Can you guess what the main 4 elements are? What do you think is most abundant in living things? What's one? Elements, Jack, elements. What? No? Oxygen's one of them. Nitrogen's one. Hydrogen. And the biggest one? Carbon. Carbon, hydrogen, oxygen, nitrogen make up over 98% of the mass in living organisms. And 3 out of the 4 are gases at room temperature. So in biochemistry, often what we're studying are things that we call organic compounds. Now don't confuse the word organic with what you might think of in farming or the grocery store. It's not related to that at all. In chemistry, organic means the compound contains hydrogen and carbon. It contains both of them. If you have older brothers or sisters in college, you may have heard them complaining about their organic chemistry class. Has anyone heard about that before? Typically, people see organic chemistry as one of the most difficult classes they take in college. It is a class in which you study this vast array of compounds that have carbon and hydrogen. It involves often lots of memorization of formulas and structures and so forth. But organic chemistry, typically these organic compounds are produced in living things. Okay? Living things produce these. However, sure. So, remind me, who was the scientist that showed that there could be exceptions to this? That living things make organic compounds. Anybody know? Who did an experiment in which they showed you could have inorganic compounds and they could spontaneously, given the right conditions, form organic compounds?
Albert Einstein.
Miller and Urey in that apparatus with the electricity
I'm
and
not ready, but that's where I put it.
so the four main groups that we're going to study of organic compounds are carbohydrates, proteins, lipids, and nucleic acids. We'll spend some time in each of those categories. But inorganic compounds are also important in living things. Okay? Inorganic compounds, they might have carbon, they might have hydrogen, but they do not have both. Water, for example, has hydrogen, but it doesn't have carbon. Carbon dioxide has carbon, but it's missing hydrogen. It's inorganic. So something is organic if it has both carbon and hydrogen, inorganic if it's missing one of them. Then it's still inorganic. So if you look at a human, the elements that make up a human, carbon, hydrogen, oxygen, nitrogen, that's 96%. The other important elements that make up less than 4%, calcium, phosphates, potassium, sulfur, sodium, chlorine, magnesium. And then there are these which are found in very, very small amounts. Trace elements that are found in living things. All right, let's finish up here with just by talking about chemical bonds. So when atoms have this attractive force between the electrons, or due to the electrons in the valence level, they can form bonds. Okay? And these bonds represent stored energy. To create bonds, it often takes energy to do that. And when those bonds are then broken, the energy can be released. And living things use that principle to sort of store and harness energy. We'll talk about two types of bonds, really. Ionic bonds and covalent bonds. Ionic bonds, where have we heard this? Ions. Ionic bonds form between ions. So ions form when an atom gains or loses an electron. Here's an example, sodium and chlorine. So sodium, how many valence electrons does it have?
One.
Just one. What would it like to do?
Give it away.
Get rid of it. Because then its next level would be filled, it would be happy. Chlorine, how many is outer shell? 7. It would like to gain one to have a full outer shell. So sodium gives away an electron to chlorine. Then they both have full outer shells, they're both happy. But now they both have a charge. What will the charge of sodium be? Since it got rid of an electron.
-1.
It got rid, it'd be positive. And chlorine gained an electron? Negative. Positive and negative charges are attracted, just like opposite poles of a magnet are attracted. And so then, these two ions, sodium and chlorine, are attracted to each other and they form an ionic bond between each other. That's how ionic bonds form. You have these charged ions, they form this bond. The other type of bond is something called a covalent bond. Valent as in valence electrons. Covalent bonds are found when atoms share their electrons. So here's an example. This is methane, CH4. So carbon has how many electrons in its valence shell? Nope. Carbon has 4. What would it like to do? Get 4 more. How about hydrogen? How many in hydrogen's valence level? Just 1. What would it like to do? Not quite.
Share.
It would like to get an extra one because 2 would be full for it. So carbon needs 4. Each hydrogen atom wants to share one. So 4 hydrogen atoms each share a single electron with carbon. And then if we look at the total electrons, carbon now, because it's sharing these X's, it has 8 in its outer shell. Each hydrogen now has 2 in its outer shell, which is full for hydrogen. And therefore it all bonds together and we have a compound called methane. These bonds, when the electrons are shared, are called covalent bonds. They're sharing. Here's another example. Carbon dioxide. Again, carbon has 4 electrons in its outer shell. How about oxygen? 6. What is oxygen looking to do? Get 2 more. So if these 2 electrons from carbon are shared with an oxygen, and these 2 are shared with another oxygen, the oxygen has 8. The carbon has 8 shared electrons. Again, they're both stable. They both have full outer shells, and we have carbon dioxide, a compound.
Wait, can you explain why a hydrogen is from the
Yeah, because that hydrogen only has, normal hydrogen has 1 electron. And that first shell, because it's so small, only holds a maximum of 2. So to get to 2, it's filled up. Every other element has to get to 8. All right, last thing to talk about. What we've been talking about are these molecular formulas. When we say CH4, H2O, C6H12O6, those are molecular formulas. They just are telling you the ratio of one type of atom to another. Another way to show the atoms is in a structural formula. This is also showing methane, but this is showing you how those atoms are actually connected to each other. The other way we can depict it is using an electron dot formula, which shows the shared electrons between those atoms. All right. I'll just mention this quickly. So bonds can form that are different than these single covalent bonds, double bonds, triple bonds, quadruple bonds. They're not as strong, and they hold less energy than the single bonds between 2 electrons. Examples, ethylene. Ethylene is a gas. It has a double bond between the 2 carbons. Have you ever heard that if you put like a banana in a paper bag with like an unripe peach, it'll make like the peach ripen fast? It actually works. Because as fruit ripens, it releases this ethylene gas, and that encourages ripening in nearby fruits. In fact, usually fruits are shipped unripe, like a bunch of green bananas are shipped, and then they add ethylene gas to a container, and that causes them to start to ripen more quickly. Acetylene has a triple bond between the carbons. This is used in blowtorches that are used to like cut through metal, and acetylene torch is made with this. Diamonds, graphite, pure carbon is just carbon, and there is a quadruple bond between the 4 electrons in these different carbon atoms. So these are all different types of bonds. Gabe?
I noticed that, however you say that, the one that starts with an A.
Acetylene?
Yeah, it kind of sounds like acetylcholine.
Yeah, they're related. That acetyl is our functional group. All right, if you need to get further study, I'll go ahead.